Hi there. I'm down on the floor today for Boombot V2 Season 1 Episode 5 Encoders and Interrupts. And yes, this is take two. Take one didn't work out so well. Anyways, this is part of BCIT Technology Teacher Education's TTED 5060 course, where we're making a project called the Boombot, an introductory project built from scratch, all about robotics. And today we're taking a look at encoders and interrupts. Let's get started. Okay, so one of the things in a lot of robotics competitions is that you'll start with an autonomous period where the robot has to go out and accomplish something on its own without the drivers helping out. And so this is an example of what we call dead reckoning navigation. Now, in some of your previous exercises, you used a little bit of dead reckoning where you used a time delay to get the robot to go out and do a certain task. And that works okay. You know, if you're just starting out and that's what you do in your first year, then you're doing okay. But sooner or later, you want to upgrade it a little bit so you can drive with a little bit better precision. And here on the floor, you can see I've laid out two tape lines exactly 1 meter apart. And when I push a button on my robot, it's going to drive out there and it's going to stop 1 meter away from me right now. And if I do that again, it's going to come out there and stop exactly 1 meter away from me. And if I do it again, it's going to stop 1 meter away from me. And well, you kind of get how that's going to work. I could do it again, and it's going to stop 1 meter away from me. Now, the nice thing about this is that when you're trying to get a robot into a certain position, you can do this fairly simple with some fairly basic equipment. And we're going to take a look at some of that basic equipment and how it's installed on your Boombot and how you're going to write some code to make it work. So let me just get these screens shifted around a little bit, and, and interrupts is what we want to talk about today. So I brought the robot up here onto the desk, and you can remember when you were putting this all together, you were installing these little things inside called encoder rings. And the instruction said it was really important that you made the outside of them white and not the valleys down here. We didn't want those to be white. We wanted them to be nice and dark black. Well, you probably, after doing the edge detection and line following lesson, probably realized that that's because we have a QRD 1114 sensor right down here. And let me just turn off this light because just like the QRD 1114s on your edge detector, if you take a look at them with a camera, you can see that infrared light glowing in the infrared LED in each of your QRD 1114s. Okay, now kind of gets washed out when I turn the light back on there, but it illuminates everything else so nice. So we've got these rings set up right in here, and they're on the same drive shaft as the motor, so they rotate around. And up until now, the only thing we've mentioned about them is that when you're building your robot, you don't want to hear clunk, 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 because that flips down there, and we don't want this interfering with them. We want this sitting about 1 millimeter off the surface. And again, after talking about the the edge detectors on the front for line following and how they work optimally at a distance of about 1 millimeter, you probably now know why we wanted these sensors to be 1 millimeter above this platform. Now, looking at our sketch of how this is all set up right in here, you'll recall that the sensor that we're using in here is a phototransistor. Okay, let me just bring that down a little bit right in there. Okay, so we've got a phototransistor right inside here, and the phototransistor picks up reflected light coming off those white sections of the encoder ring. And we've got 6 sections on the encoder ring, and hopefully your encoder ring doesn't have this ugly oops in the drawing that I put in mine. Okay, and so there's 6 sections going all the way around there. And there's light being bounced down here from an LED, reflects off here, and when it's getting reflected into that sensor, it comes in right here and it closes the circuit on that phototransistor because it's like the base. So when the photons come in there, they hit the base and it's almost like there's a tiny little photocell in there that picks that up, turns the transistor on, and allows electricity to flow down through here. So you've got +5 on this side. It flows through your resistor right here. The robot was complaining because I was ignoring it. It flows through the resistor right here. And if light's hitting this, then it flows through here very easily and comes to ground. And if there's no light hitting this, then it really doesn't flow at all. And whether light flows through here or not determines whether there's current flow. And that determines whether there's current flow across the resistor and whether there's a voltage drop across the resistor or not. So when we've got white right here, the white hits here, current flows to ground, pulling this pin low. And this is, we've got tied into an Arduino pin. Now on our edge detector, we had it pretty easy because that was tied in to an analog pin. So we could take an analog reading off of that and find out exactly what voltage that was at. Well, we've got these tied into a digital pin because we need them to trigger an interrupt, and we'll talk more about what that is a little bit later on. But this goes back to our Arduino on pins number 2 and pins number 3, because one from each side, because that is how our where our interrupt pins are located. Okay, now a few other things to keep in mind. Our wheel, if you measure it, is about 63 millimeters in diameter. So that means that if you take a look at this, the circumference of that wheel will be pi d, or 3.14 times 63 millimeters equals 198 millimeters. My experimentation, you can probably add a few more decimal places to pi, and it might actually be 63.5 millimeters. So you might be actually closer to 100, closer to 200 millimeter diameter wheel. You'll have to play around with how your robot is configured to get that reading. But if we go off the raw readings, you've got 198 millimeters of circumference for your wheel divided amongst the 12 pulses on the encoder means that you're going to get a 16.5 millimeter distance traveled per change pulse. What do I mean by a change pulse? Well, let's take a look right in here at the signals that we should be seeing coming off of our QRD 1114. Now, when it is light, right in here, we have light bouncing in here. The phototransistor is on, so we have current being conducted down to ground, and this pin is pulled low. Now, we don't go all the way down to 0 volts. Okay, there is a little bit of a voltage drop across that phototransistor, but darn it, we're low because that voltage drop is a lot lower than the voltage drop you see across the 10K ohm resistor. Now, when there's no light flowing across there, you're going to see that voltage suddenly rise up in here. Okay, and so when it's dark, it's going to come up high. And then the next disk is part of the encoder disk will come along and it'll be light again, it'll go low and it'll go high. And we should see a nice little pattern coming along right like this. Now I've drawn it as a little bit of a curve right here at the top, and we'll take a look at it using your oscilloscope to see why it's curved at the edges. As this edge comes along, it starts to get a little brighter and then it starts to get a little darker, which is why we've got the edges kind of rounded off like that right in there. Okay, and we don't quite get all the way up to 5 volts, but we do get outside the dangerous 2 to 3 volt range. Okay, between 2 to 3 volts, if you do a digital read on here, the Arduino doesn't really know if it's high or low. Okay, once you get above 3, it's pretty sure that it's high. And once you get below 2, it's pretty sure that it's low. But if you're just sitting in here at 3 volts, it's not 100% sure. So we got to make sure that we get our signal up over the 3 volts. There's 3 types of signals that we can measure when we take a look at this. We can measure a rising signal where the slope is coming upwards this way, so going from a low voltage to a high voltage. We've got a falling edge, okay, where it's coming down from a high voltage to a low voltage, or the change is when we have either a rising or a falling edge on there. So you'll see all three of these terms used with our interrupts in the Arduino. Rising mean a voltage coming up, falling a voltage going down, and change, it's either one. It's just transitioning from high to low or from low to high. Okay, so those are some of the terms that we're going to take a look at on here. Now the encoder we're looking at and that we're using is a very, very simple encoder. There's another type of encoder called the Quadrature Encoder, okay, that is actually more common in commercial systems. And if you buy a pre-built encoder, it's probably a Quadrature encoder. And the Quadrature encoder actually has two different sensors. One sensor will be positioned right here, and the other sensor will be positioned right here. And we'll call this one A, and we'll call this one B. Okay, now if you've got those two sensors in there, and you've got an edge sliding along towards those two sensors, let me just grab a, here comes our edge towards those two sensors, da, 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 da. Okay, which one's going to turn on first? Well, if I'm moving in this direction, A will turn on first. Okay, because I've got the two sensors in there, slightly off space, I can tell which one's going to turn off first. But if I'm moving in this direction, B will trigger first. And what you'll get with a quadrature encoder, it takes two inputs to your Arduino to be able to measure a quadrature encoder. But what you'll get is pulses coming along just like so, about what we'd get off of our regular encoder. So that is if you just read A, but if you then come along and also read B, and you see it looking something like this on B, that tells you B is triggering slightly after A. Okay, and so if you see that pattern, you know that A in pencil is getting triggered just before B in pen. So your wheel is spinning in this direction. And if you see it triggering the other way, where, you know, let's just take a look at one pulse right here. I don't need to write all that out again. Where what happens instead, if B comes up and triggers first, okay, and turns off first, well, now B is phase shifted a little bit to the left, and that means that it's coming in this way. It's triggering B, turning on B, and then turning on A. So when you watch your encoders in this case, when you see a rising edge like that, you can take a look and say, oh, is B triggered? Well, when A triggers, if B is already triggered, you're turning in that direction. And if B hasn't already triggered, then B is moving in that direction. So the quadrature encoder is a nicer encoder. It's the sort of thing that you'll typically get if you're buying a commercial pre-made encoder. You'll also tend to get a lot more crisp, nice edges like that, because instead of using a reflective encoder, a lot of commercial encoders will use a disc with slots in it, and they'll use a transmissive sensor. So what you'll have in a transmissive sensor is you'll have a base, something like this. Actually, those would be joined together. Okay, so in our case, our circuit board would be right up here, and our LED would be down on this side, or the other side, doesn't really matter which side the LED is, and it would be transmitting light over to our photodiode on this side. Okay, so the light's coming right through there, and in the middle of that, you would have a disc with slots in it, and that disc would be spinning around. And as that disc with slots in it, those slots pass through, you would get a nice little pattern like this. Makes it really easy to integrate two light sources and two sensors to create your quadrature encoder and have your disc spinning this way through it instead of having a reflective object sensor. If you're interested in doing that on a board at any point or experimenting with that, it's pretty easy to find these types of devices. Let me just show you what they look like. Encoder, and this is called a photo interrupter. And typically, if you're dealing with an encoder, instead of using a reflective sensor, you'll use a transmissive sensor. And you can see these ones are kind of U-shaped, and that's because you run a slot right down the middle through there. And so right here, they've got a nickel to give you a size reference. Think of this as a slot, as a disk, but it's got a whole bunch of different slots in it. And as that spins around past there, the slots allow the light to come through. And that's a little more precise way of doing it than what we have over here with the reflective sensor. You get crisper signals. You can see I've kind of rounded off the top and the bottom right here. And we'll take a look at why I've done that when we take a look at some readings with our DP scope. But if we were using a photo interrupter circuit and we were spinning a disk between them, it would be very precise and very sharp transitions. So technically, if you're designing something from scratch, the photo interrupter is a slightly better sensor than a reflective object sensor. Considerably better sensor in many ways, but they cost a few dollars more, take a little bit more space underneath the robot, and I didn't have room for them, and I was trying to keep the cost low, so I saved a couple bucks by going with with a reflective sensor, and the exact same sensor that we already used down in the edge detection board, so you only have to keep one item in stock. But anyways, we've got our DP scope software up and running over here, and we've got our Boombot right down here, and we need to hook up our DP scope into our Boombot. And of course, it's critical anytime you're using any kind of oscilloscope that you have a ground connection to your circuit. And so for an easy ground connection, I've just grabbed a piece of wire right here, clipped it onto the DP scope ground, and I'm just going to insert that into right here. There we go. Okay, now next, I'm going to take my channel 1 signal lead and I'm going to hook it in to this resistor right here. Now, this says R7, okay, and it is a 10K ohm resistor. Let me hold that in. I think we can get it right there. And if we hold it just right in there, you can see that R7's lead comes right off here and it goes to a trace on the circuit board that connects to the QRD1114 and then comes back down here and comes underneath and goes inside and connects to the Arduino somewhere in there. The point that we want to sample our signal from is going to be right there. Okay, so it should clip on and hold really nicely there on the QRD 1114 side of that resistor. That's that intersection point where we should see the voltage changing, and that little trace that runs along the board should take that signal right back to the Arduino. Okay, if we've got that set up right there, I'm just going to try this out using the USB port to power it all up. So I'm going to come in here and give it some logic power, and we're hooked up right there, and it boots up, and it would really like to run if it could, but I've got the motors turned off, so it's not going anywhere on me right now. I'm going to come over to the DP scope software, and I'm going to click on the run button. Now, right now I'm not using channel 2 for anything. If you did want to use channel 2 for something, the equivalent place where you'd hook it up would be over here on R11, which is also a 10K resistor. And on R11, for the right side of the robot, you can see a little trace on the printed circuit board comes right down in here, connects right there, and then goes back to the Arduino in there. So you could connect on the QRD 1114 side of R11. Okay. So we can sample either encoder, and we do want to make sure that they're both working nicely. But for right now, for simplicity's sake, I'm going to turn channel 2 off. I'm also going to set this to 1 volt per division because that makes it really easy for me to know that I'm at 2 volts right now. Now, as I turn the wheel, you'll see that voltage bumping up and down really rapidly on the DP scope. Well, that's because I'm fluctuating from having the dark section to having the light section, reflecting light back into that sensor, and I'm bumping the signal from low to high. Now you'll notice that when we go high, we don't go all that high. We just barely make it up above 3 volts on there, okay, at 1 volt per division. Oh, actually that one made it up above 4 volts. doesn't go all the way to 5. We've got 1, 2, 3, 4 volts right on there. So that's a pretty nice clean signal. 4 volts, that's going to trigger as high. The Arduino should be able to count that no problem. Now, when I spin the wheel manually, you'll see that bouncing around, but it's showing up as a really flat line. I need to change my time divisions down here, and I've found that 50 milliseconds per division works really nice for reading this. And so if I spin it around right in there, I start to get some nice peaks and valleys. Okay, so as you're spinning your wheel, you should see some peaks coming in there like that. Now, I've already gone through and adjusted the height by adjusting my spacers back here. Okay, I didn't actually adjust the spacers back there, I did it all at the front. But if your spacers at the back are reasonably spaced on the board, then you can probably adjust everything that you need to right in here with the nuts right at the front. You can use washers, you can use spacers, you can slip a little shim of a piece of cardstock in here if you want to be really fine. And let me just drop that right down in there. And I took one nut off, so this comes down a little bit lower. Now, spin the wheel manually, listen to it carefully, make sure nothing's rubbing on there. And if you're doing that, then you might see that the pattern's not working quite as well this time out. I'm going to turn on some power right here, and I want to see what that looks like when that wheel's running. Make sure my wires aren't touching the wheel and that I'm holding this up off the desk so it doesn't try and drive onto the floor. Press a button, start the wheel, and there you can see a pattern, and it had a whole bunch of little spikes and noise in there. I wasn't very impressed with it, but it disappeared before we wanted to see it. So what we're going to do so that we can record that is we're going to use a channel 1 trigger, take it off of auto trigger, set your DP scope to channel 1, and then set your trigger height at about 2 volts. Okay, now go ahead and run your robot again. I missed a few of them on there. There we go. So that's coming through pretty quickly. If I went to a slightly longer time division, I'd see more of those spikes on there. There you go. And it captured the last few of them. I should do fewer spins on here because we see that, and then it goes to catch the last few. I could adjust that and what I'm taking a look at right on there, or I could go down to 20 milliseconds per division. You can play around with your settings. And now the peaks are a little further apart, but you can tell a couple things in here. They're all taking roughly the same time, but look at some of the noise and gunk that I'm getting in right here. Now, I don't have a great explanation for what exactly is causing that noise and gunk. Maybe I didn't fill in the white quite as white on one of the sections. Maybe the 3D printer is more reflective than I thought it would be. But what I have found is that if I get the height of that sensor off of the encoder ring absolutely perfect, I don't get those flaws. And so on my robot, the trick is to add a third 440 nut on there. Now you could use a combination of nuts, spacers, whatever you need to get the bottom of this board the exact right height off of here so that you can see when it spins that your signals look nice and clean like that. Okay, see the difference between having your board at the right height and having your board at the wrong height? Nice clean signals versus ugly signals. Now, one of the neat things about using the oscilloscope is that we can actually see the time in between the pulses. I'm running this at 20 milliseconds per division right now. And so this is 20 milliseconds, this is 60 milliseconds, or sorry, 20, 40, 60 right over to here. So in between those pulses, I'm seeing a little bit more than 60 milliseconds of time in between them. And so if I've got 6 pulses for 1 revolution, then it's taking me about 360 milliseconds for 1 revolution to happen. I'm going to see if I can adjust my horizontal position on my X just a little bit here. I'd like to see a little bit more of that data preserved for me. Um, let's do a single shot right here. Turn on your single shot and try it again. And that'll capture one screen of data for you. So you can see that at 20 milliseconds per division, this is 10 divisions, this is another 10 divisions, so 20 divisions, so 400 milliseconds across the screen, or 0.4 of a second. And I get 1, 2, 3, 4, 5, 6. So about, yeah, 360-ish milliseconds per revolution. And you can use that to determine the speed of your wheel. So right now I've talked about using the encoders for measuring distance, but inherent in measuring distance, since we can also measure time, well, distance divided by time gives you your velocity. So you can use these to measure and help control the velocity of your wheels as well. So all sorts of neat stuff going on in right there. Now, one of the reasons that this works better than time measurement for managing your robot is that sometimes when you're running the robot, the batteries will start to die. You're trying to do dead reckoning and you go out there and you've got a really supercharged battery, so you're traveling a little bit faster than when you did using your slightly dead practice batteries. So using time measurements, your positions can be all the way off. Maybe there's a headwind. Maybe your motors aren't quite as low friction today. Maybe all these different little differences. You're on a different surface. I'm going to just hold on to this right here, and I'm going to show you what this looks like when your motor tries to run with just a little bit of drag on it. Now keep in mind that here we got 6 pulses in per 400 millisecond screen. We'll run that again with a little bit of drag on it. Oh, sorry, I need to set that up again and tell it that I wanted another shot on here. Let's clear that, run that, and with a little bit of drag on there, you'll now see that on that 400 millisecond screen, I see 1, 2, 3, 4, 5, and the sixth one doesn't quite get on there. So my motors were running slower because my encoder was seeing longer pulses in between each one of those colored bits coming by on the encoder ring. So encoder is great for speed measurement, but also really good for distance measurement, because when you're counting those pulses, it doesn't matter how fast your wheel is turning. You're going to count the pulses, the actual outcome, not the time that was the estimate of it. Okay, so important that you take an oscilloscope or your DP scope and you get this hooked up, and you want to see nice smooth pulses right coming along here. You don't want to see all those jaggies and random fluctuations coming up and down. If you're seeing that, it's probably a sign that you need to adjust your height on the control board relative to your um, encoder rings. So once we've got the height all set up properly, and we're going to use the oscilloscope to do that because you've got an oscilloscope, but there might be people out there trying this who don't have an oscilloscope. I'm going to give you some software ways to kind of estimate it. It's not quite as good as being able to look at the raw data coming in, but we can make it happen. Now, because we're adding a new sensor to the robot, we also have to add some new terms in here, okay? And so we've already got a whole bunch of terms in here. Let's go through and take a look at the new ones that we're adding. In the last time out, we added the left edge and the right edge sensor. So today, we're going to add a couple of sensors and a couple of variables right in here. So again, this is in the declarations and definitions part of your program. Before you get to void setup, we're going to tell it that the QRD 1114 sensor, counting our left pin revolutions, is connected to pin 2, and that the one connected to our right encoder is connected to pin 3. And then we're also going to create a couple of unsigned int variables, because we do need fairly large numbers to keep track of how many times they go around. And we're going to call one left count. We're going to start it with 0 in it. We're going to have right count with 0 in it. And those ones are just going to be running in the background. And when we take a look at the interrupts, they're automatically going to increment for us every time a pulse goes past. It's going to be kind of magic how we make this work. Interrupts are really cool. Before we get to interrupts, however, if you're just testing to make sure these work, put these definitions in right here. And then come down. All of your setup remains the same. You don't have to do anything special in setup right in here. And in void loop, get rid of everything except for these two lines. Okay, now we're compacting two things into one instruction statement right here. Okay, we are going to do a digital read of your left encoder. Okay, now when you do a digital read on an object, it will come back as either high or low. So if we've got light shining on the phototransistor in there, it's going to be conducting, there's going to be a voltage drop across the resistor, and we will have a low signal coming in here. Okay, and if it's dark, then it won't be conducting, this will be high. So what we're then going to do is we're going to take that low or that high, and we're going to pass it off to a digital write, and we're going to hand it off to the left side LED. So if this pin is reading high, this pin will also read high. And the same thing down here for our right LED and our right detector. So I'm going to go ahead and I'm going to send that up to the robot. It compiles, it uploads. And now what we've got on here is the robot starts up, and you can see I've got a glowing LED. We'll just start with the left side right here. Might work better if I turn that light on and I'll adjust. And there you go. You can see that LED. As I turn the wheel right there, I've got the LED flashing on and off as the status of that Arduino pin changes. And if I do it fast, then I get a fast blinking LED. And if I do it slowly, I get a slow blinking LED. And it stays nice and steady even though I wobble it, a little bit in there. I need to change it, like I said, about 16 millimeters to get it to turn on and off. And you can put it down and you can roll it forwards and backwards and see what's going on in there. Okay, so that's one way to test and make sure that they're working before you get to doing all the fancy interrupt stuff. Okay, and make sure you test on the other side as well. It's kind of hidden on mine by this ESP32 cam, which is getting warm. I think it's sucking a lot of current out of there and busy transmitting video out to the Ethernet. Okay, and if I turn this side, it's flashing on and off at a fairly nice even pace as well. So that's a good way to keep track and just confirm that you are able to read those encoders. Okay, so always important when you're trying to make something work that you test it in little simple steps, because as soon as one of those simple steps goes wrong, that's a sign that you don't understand something, you don't have it working right, and there's no sense going on to build everything else that you're trying to do on top of a faulty foundation. Okay, so if you've got this part working right now, and when you push it forwards and backwards, you can see the LEDs flashing. Okay, that's a good sign that the signals from those encoders are getting back to your Arduino right here, and your Arduino is going to be able to do something with them. Let's take a look at what we want the Arduino to be able to do with them. Okay, so now that we know we've got our encoders working and that we're able to see them by detecting the flashing LEDs on the front and rotate the wheels around, we've checked them on our oscilloscope to see that we've got nice smooth wave patterns, and we've got an idea of how those patterns are going to come in a little bit faster as the wheels spin faster. And we've seen that little bit of curve part at the top. That'll set you up to understand how some of this code is going to work. Okay, now I've added a few more things to our declarations and definitions right up here. So we already had the encoders in there, and I can't remember if we had the left count and the right count variables in there, but these are the variables that we're going to use to keep track of how many ticks go by. And keep in mind that because we're going to use the change setting, there's six there's six transitions on the encoder ring. So from low to high is one change, high to low is down to the other. So we'll get 12 of these ticks per revolution. Okay, And that means that each 16.5 millimeters of wheel travel should give us roughly 1 tick. Now, we do have a couple other things that we need to do just to filter out errors. And I'm going to talk about the error filtering in a little bit, but don't panic. The last left interrupt and the last right interrupt and the fastest possible tick are here to help with the error filtering. And basically what we're trying to eliminate is any weird transitions that happen in between while you're going from low to high. In that no man's land that I was talking about, once we detect a change happening, we just say, okay, don't take any more until that transition's completed. Because we know the maximum RPM of our wheels, we can say that the ticks can't come in any faster than that. And if you're sending me data faster than that, it's bad data. So we'll take a look at how to filter that out. But before we get there, we need to talk a little bit about interrupts. And these commands right here are critical to making your interrupts work. So let me just scroll that up a little bit so you can see all the comments on there as well. So attach interrupt command is what enables the interrupts. Now, the interrupts are a hardware feature built into the chip on your Arduino. Okay, you've got no control over the fact that they need to be hooked up to pins 2 and 3, and they're referred to as interrupt 0 and interrupt 1. If you delve into the Arduino data sheet and you really get into that mega microcontrollers, yes, there are more interrupts, and yes, there are more options available. No, we're not talking about them today. We're talking about interrupt 0 and interrupt 1 attached to pins 2 and pins 3, because that's how this chip was designed. By chip, I'm referring to the actual little app mega chip that's making the Arduino work. Okay, so what we're saying right here is that this digital pin to interrupt is what translates between saying pin 2 that I've got right here for left encoder, it translates that into interrupt 0. So it's just an Arduino coding thing. We could put 0 in here, but this way, if we change it to a different pin or you move to a different microcontroller, it's more translatable, and it follows the example, if you look in the help file, of having digital pin to interrupt as the recommended way to write this code. So basically, this is saying which interrupt is going to trigger the interrupt. This command says what to do. It's going to run a function called count left, and this is called an interrupt service routine. You'll see it referred to as an ISR in some of the help files, and I'll show you the interrupt service routine. I've written it further down in the code, and I've called it count left. And finally, this tells it that it's going to happen when there is a change in the state. This could be rising, it could be falling, or it could be a change, which is either rising or falling. Okay. Oh, I should change my comments on there. I've been developing this code over the last day or so. It's going to trigger it when it detects either a rising or falling edge on the encoder pin. We just get a little more precision using that instead of only just the rising. Now, what is an interrupt? If you think about a lecture, okay, and a student raises their hand in a lecture, okay, that's what we call an interrupt flag. You're the teacher, you're the main program that's run, or you're the microcontroller that's running the program in the class, and you're going around and you're doing your thing, and you're like, you've got all this code, your notes and that you need to get out to the students over the course of the lecture, and you're working down here and you're following the program, and then bloop, an interrupt flag goes up in your classroom. And so what you're going to do is you're going to finish your sentence, you're going to finish your topic, you're going to wait until you're ready. And when you're ready to handle that interrupt, you're going to say, yes, do you have a question? And the student's going to say, can I go to the bathroom? 9 times out of 10. Anyway, they're going to have a question for you, and you're going to handle that question according to your own interrupt service routine. No. The bell goes in 10 minutes. You can wait. So you can handle the interrupt really easily sometimes. Interrupt service routines need to be handled quickly, okay? Because you've got your main program right here and you've got all your material that you need to get out to the students. And if the interrupt service routine goes on too long, you've interrupted the main code and you've caused a problem. So you need to have really, really quick and efficient interrupt service routines. Okay, so what we're saying is that we've told the Arduino when it sees a change of state on pin 2, raise a flag saying, excuse me, sir, I'd like an interrupt when you get a chance. And the microcontroller, okay, is going to sit there and it's going to keep processing. It says, I see that interrupt. And it goes down and it says, what do I do when I see the left hand raising an interrupt? Well, I am going to come down to the function called count left. And count left is all the way down at the bottom of this code. And count left comes in here and it first thing it does is it says, how long has it been since the last time there was an interrupt? Okay, because as I was saying, during that transition, as the wheel spins from high to low, you can sometimes get a whole bunch of fake phony little interrupts coming along and blah, 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 blah. And we don't want to count the fake phony ones. We only want to count that one transition. And the transitions can't happen any faster than about once every 20 or 30 milliseconds. So we come in here and we say, well, if our time in millis minus the time that the last left-hand interrupt happened is greater than the fastest possible tick, so then it's probably a legitimate interrupt and we're going to have our left count increment by 1. So we're going to say, there was a change, count it, carry on with the program. Okay, and then we're going to say, okay, that was the time that the last one occurred, so that we're going to wait another 30 milliseconds or 20 milliseconds or however long we've got set up as the fastest possible tick, which we set up earlier in the program. And there we'll handle it. And you'll see that the right-hand interrupt is exactly the same, except we use right as a word anywhere we had left down here. We increment the right counter. So what this should do is you'll notice that you don't call these routines from anywhere in your program. Okay. In fact, our main loop right in here, void loop right here, doesn't call those functions at all. It just comes around here and it just keeps printing these things out with a delay statement. And in our normal operation of code, if we didn't have interrupts, this would just keep printing out the same number over and over and over again, because in your entire void loop, there is nothing to change that variable left count or right count. But we did the attach interrupt things, and we've got these interrupts running in the background. So let's take a look at what happens when we upload this code to our robot. And let me just put this right here. I've taken a very faint felt pen mark and marked it on that wheel. Okay, and you can mark it on the rim or something if you prefer. I'm going to turn on the serial monitor. Serial monitor. This is the version 2. Didn't want to do that. Version 2.0 of the Arduino IDE. So my serial monitor pops up right down in here. And let's come back up here. You can see it's printing out left count, right count, left count, right count. And now what I'm going to do is I'm just going to hold this nice and flush to the tabletop. And I'm going to watch that. And I'm going to do one complete revolution until that tick comes right back up to the top. And it should be saying 12. And when I look right over there, it tells me I went 12 ticks. So we just went 12 ticks, and I wanted to do that a couple more times because I was actually getting a bit of glitching, and you probably noticed right at the end of that last clip of the video that the time between when it was displaying on the computer and when it should have been reading from the Boombot was getting mixed up. And I'm going to blame some of that on that fancy new Arduino IDE 2.0. It seemed to be lagging, and I recorded a bunch of other video segments, and it seemed to be causing me grief. So let's go back to classic Arduino 1.8 and use its serial monitor. And let's take a look right on here. And there we go, we're up and running. We're at 0, and you should be able to do this a couple times to get some reliability. There's that little black mark right on there. And let's roll it forward 1 revolution. And don't go too slow. And there we go, we're getting much lower latency in our data. And we should be able to roll it backwards 1 revolution. And oh, I think I went a little too far. Yeah, you can see on this side I got 25 ticks instead of 24 because it should be 12 in each direction. Let's go forward. And there we go, 35 and 37. Come back this way. There we go. And oh, now there you can see one of them has just gone crazy. And so I must be right on a boundary. If I turn it like that, it starts behaving again. Remember, we had that little curve area right in there that we tried to filter out, all of those where we say the fastest possible tick. Well, there we were just sitting right on that curve. And that's one of the advantages of having the slot encoder and the photo interrupter is you're less likely to get that. So there is still a little bit of imperfection in this encoder. If you buy a commercially made encoder, you're not going to run into that problem. So when you're building bigger robots, you're not likely to see that happening again. But anyway, there you go. The encoders are now up and running, and now it's up to you to come up with something intelligent to make your robot go 1 meter. Okay, so where would I start for trying to go 1 meter? Well, first of all, I am going to put this code up on D2L for you as it stands right now. Now, inside your loop right here, you're going to be able to get rid of that. You can probably get rid of the delay. It doesn't matter all that much. And you're going to be able to put some conditions in here for what you want your robot to do. Now, I usually like to start with um, a while loop in here. And I just like to come in here and say, while, you see this in some of the other code, um, analog read of button pin. Now this is where I do miss the fancy 2.0 is now I have to go and check, did I spell that right? Was all my capitalization right? Button pin, yes, button underscore pin is A2. While I do an analog read of that pin, and while that's less than, I've said less than 10 in the past. Sometimes that still glitches a bit. I might say less than 20 right now. So while there's no button being pressed, okay, it's just going to hang out right here, okay? And then when the button is pressed, the first thing I'm going to do is I'm going to set left underscore count equal to 0 and right underscore count equal to 0, okay? And then I can do another while statement in here, and I can put in a while left underscore count is less than however far I want it to go. Let's say 100, let's say 60. 60 is pretty close to a meter on your Boombot. You might have to tweak it a little bit. Okay, we're going to do this thing while left count is less than 60. You're going to drive, and you can set your speeds in here. Now I'm going to say forward, comma, forward. But we know that forward is a keyword for 255. If your robot's traveling off to one side or the other, you might want to change one of those numbers so that if one motor's going a little too fast, just slow that motor down. Try slowing it down 5, say 250 and 255 to control how fast your motor is going. And you can say while left count is less than 60, drive straight forward. And when left count exceeds 60, okay, then you can come in here and you can say stop the motors. And it's halt, comma, halt to stop those motors. Okay, and your robot should come to a stop right about where you want it to be. Okay, then it'll come around here, it'll print out what your count is at, and then you'll come right back up here and you'll start the code all over again. No reason you couldn't tuck that code right into there. Let's see what that looks like if I upload that onto the robot. Done uploading. So now it's just waiting for me to push a button, and I push the button. Oh, it's going to work a lot better if I turn the motors on. And it should run around. And it should be recording those pulses. Let me restart that. Something went wonky because it wasn't running. Okay, and let's start that. And it should have stopped by now. Okay, let's turn on this. Start that up and let's move that section into the loop. And let's just put a little delay in there so that we don't. Actually, let's put a 30 millisecond delay right in there so that we don't jam the serial port with too much data coming down right there. So this should happen right in here. Let's upload that code. And start the serial monitor. Turn on our motors. Okay, it's waiting for us to start. There's our count coming up. This time it works. Comes to a beautiful stop right in there. And that should be traveling pretty darn close to 1 meter every time we go out. Now the beauty is that even if I put a little bit of load onto that motor and it runs slower and you can hear it really struggling right in there, it's still going to come to a stop at 59. Now, because I didn't have any speed control over on this side, the right side cranked itself all the way up and went to 82, so it traveled further. Later on, at a more advanced level, we're going to take a look at using this for speed control. But for right now, you can do this for distance control and create some nice videos, just like we had to start this one. There you go. This is a little trickier than some of the things that you've done already. You do have to get it set up and get it into position, just like so, so that you're reading those encoders properly. Using your DP scope for that can really help you out. Once you're done, put it on the floor, drive 1 meter, take it back, drive 1 meter, drive 1 meter forward, drive 1 meter back, and you will have dead reckoning position control of your Boombot. Oh, just a minute. Stop button's over here. Good night.